Welcome everyone. So I'm gonna elaborate on Deutsch Jozsa algorithm, which is the generalization of the Deutsch algorithm which was presented a while ago. So I will be going in the sequence. It was invented and really presented by the physicists. So in 1982, Richard Feynman claimed that there might be some quantum machines or some quantum processor that can enhance a problem, the solution to the problem, and can perform it better than a classical deterministic processing. Around the same time, Deutsch put effort into the same problem and proposed the algorithm, was the Deutsch algorithm, which satisfied the famous quote which he stated in 1982. So there was a set of problems P, which were solved by a deterministic machine, classical computer, and a polynomial time. But there is a set outside this P which can be solved by a quantum computer and polynomial time, but by a classical computer and exponential time, and that's what they want to look into. So what Deutsch algorithm does is it is generalization. I mean, the Deutsch Jozsa algorithm is the generalization of the Deutsch algorithm, which is a very specific subcase of this algorithm and works only for the 1-bit space. So why this algorithm is important is because it served as a base for the further algorithms like Shor's and Simon's, Grover's, because nearly the same concept is being used in that. So the physics involved in if we try to build this circuit actually, so mainly the physical concept that are involved is called the superposition. So a state psi can be represented in eigenstate, superposition of its eigenstate, which can simultaneously be evolved when an operator is working upon them. So this was the quantum superposition was the motivation of this technique. So using superposition of the simultaneous eigenstate, we can implement a function on them which can simultaneously act on the entire ensemble of the states. So it is actually implication of linearity, the superposition, and covariance, because we don't have to decode the qubit, of course. So coming to the actual problem which Deutsch faced in 1985. So we are given a black box, a kind of a hidden oracle that has mapping from binary n space to 1-bit space 0 1. So it takes n binary values and produces a corresponding 0 and 1 output. So Deutsch was asked that if I give you this f and I'm guaranteeing that this f is either balanced or constant. Constant simply implies that it has the same value for any arbitrary input that we put into the function, and balance means in this case we are just giving it zeros and ones. So if a balanced function should produce a specific output on either 0 or 1, or we can say half of the values it returns one value and on the other half. So classically we can see that this question would require more than one evaluation for classical subcase for 0 and 1 if we input 0 and 1 into the function. So coming to the complexity, as I already elaborated this, the original Deutsch subcase of Deutsch Jozsa algorithm could solve the same problem with half the probability, and the Deutsch Jozsa algorithm can work on the n binary input and still get the result with a probability of 1. So it's completely quantum deterministic algorithm. So to visualize and experience the complexity of the problem, we can see if we have n bit string and we want to know whether for each of this value we get a output of when we apply the function on this string, we get the conclusive whether it's really constant or it's balanced. So for the set 0 1 to the n, the total number of inputs would be 2 to the power n, and if we are in the worst case, let's take the best case at first. So the best case would be half of the values on which the function returns some, let's say it returns 1 occurs first, and then the rest of the values on which the function returns 0 occurs at the later stage. So at this point, when the function goes to this stage, we won't be able to conclude whether it is constant or not, but when it gives the output on this first change to be, it would tell us classically whether it's not. So from here to here, I just need 2 to the power n divided by 2 to the power n minus 1 evaluations and plus 1 evaluation to finally come to the conclusion that this is whether it's really binary or not, when the function is constant or not. So that's the classical result. So there is a class called EQP, exact quantum polynomial time. So this Deutsch Jozsa algorithm lies in roughly in the EQP class, and this class is the same set which in the first slide I put outside the class P, because this cannot be solved by a classical computer polynomial time, but can be done by a quantum computer. So prerequisites from our course ES72206 is linear algebra. We need to know basis, vector spaces, graphs and cats. Postulates of theorem, unitarity, linearity in sample interpretation, and coming to the main part, quantum gates and quantum circuit, mainly the Hadamard and CNOT. And the most important part used in this at the later stage is the decomposition of n-bit quantum gates into single qubit gates and CNOT gate. So take it to be a kind of law for quantum circuits, which we deduce. It was a 12-page long proof. So physically, if you are building this circuit, so what we need to take care of, the first is the oracle should not decohere the state x. If it would be just simple as a classical algorithm, which we don't want. And the other is it shouldn't violate the no cloning theorem, of course. Otherwise, it would be invalid as a quantum logic. So coming to the Deutsch algorithm, what Deutsch actually observed is that if you have to check whether the function is constant or not, is equivalent to checking whether it's the Zor function of its output is 0 or not, because we can manually check the case if both are same, then the Zor would return a 0, otherwise it would return 1 in the odd cases. So if I have a function which can implement this operation, the Zor operation, then I can build a quantum gate for the same. So we begin with a 2-qubit case, 0 tensor 1, and by hit and try we are just applying a Hadamard gate to it. Hadamard gate simply gives us half of 0 plus 1 tensor 0 minus 1, which is the Hadamard applied on this, or applied on both the gates. So now as I concluded from this that I need a Zor operation, so I just arbitrarily create a Zor operation, which reversible Zor operation, which can give me a result x tensor x Zor y on the input x tensor y. So applying this on my state, which is now this. So simply 0 times I just expanded and multiplied this term, so I get this expression, which is clear. Simplifying it, and what you can observe is that I took common the factor of -1 raised to the power f of 0, which I was only able to do so because my inputs were only zeros and ones. So 0 plus 1, I mean if I consider operation x plus y is equivalent to x or y if I have x and y only as zeros and ones. So I am focusing on only the first qubit, so I can discard or trash the second qubit and the global phase, because global phase isn't observable at all. So I call the new state as psi dash. So psi dash now is, and the normalized state is this Okay, then again by some hidden tracks, maybe Deutsch performed Hadamard transform to the first qubit again, and upon doing so, we get psi dash, a new psi dash equal to this state. Now rearranging the terms, I just simplified it, and observe this lower state psi dash. So clear this psi dash. The coefficient of 0 is 1 plus minus 1 to the power f0 or f1 plus and this whole term. So observe the coefficient of the term 0, state 0 and state 1. So at the end I am taking a measurement on the first qubit. So we will observe the state 0 only when its coefficient is 1. Otherwise we won't observe the first qubit at all in the state 0. So which implies f of 0 XOR 1, f of 1 must be equal to 0. So at the end we simply are observing the first qubit, and with probability 1 we can see that it is clearly giving us this result with just a single evaluation, because I used f only once in my state here. When I applied f, I just used it once. Classical, whereas I would be using 2. So that's the advantage.
Can you go back to your previous slide?
Which?
The one before.
This?
So, no, this one.
Yeah.
So, in that one, in the last line, shouldn't that be f1 plus 0 and f1 plus 2? So it's fx plus y.
No, it's right. Because yeah, okay, there's a problem. The slide should be f of 1 modulo 2 f1. Okay, but it works for the case, because if you put f of 0 1, then the letter should be 0. So that is giving me the first case. Okay, so now we are going to generalize the Deutsch algorithm into the for an n-bit space. So analogous to the previous situation, now I have a state 0 tensored itself n times tensored 1. So similarly, using the same analogy, I apply Hadamard to all the states, which clearly gives me this. Last is 0 minus 1, and the rest of the terms are simply tensored into this notation. Where my x state is represented by this binary notation. So again I apply the state uf to this, the function uf to this state, which depending on this term state x, which gives me f of x plus modulo 2 addition 0 minus 1 XOR f of x. I actually discarded the XOR 0 here, because XOR 0 you can discard, because if f is 0, that would be 0 at all in the either case. So depending upon the terms of zeros and ones, I get this f of psi dash. So again simplifying this state for specific cases of 0 and 1, I can clearly see that from the last term, if you put f of x as 1, so it would give me state 1 times, if f of 1 is 1, then 1 minus 0. Okay. And in other case, so then there would be 1 outside common, and in other state when f of x is 0, the first would be 0. So 0 tensor 0 minus 1. So I pulled up the minus 1 factor outside, raising it to the power of f of x. Again I am not concerned about the second qubit and the global phase, so I am trashing it again and rearranging the terms. After applying the Hadamard gate to the first qubit, I get this state psi of nu. Psi nu I obtained from calculating this using this operation, because suppose I have a I have psi equals applying Hadamard on a single state gives me this single term, because if you check the values of x 1 and y 1, putting them 0 and 1 and summing it over, you will just generate the same state which you get. And you are getting this term, each of the terms. So now we multiply it, because we are applying the Hadamard gate on each of the qubit. So 0 itself cancelled n times and Hadamard is applying on them, so we get these terms n times. And again we are using this binary Zoll operation, which is summation of xi by I, which is only possible because my x and y's are zeros and ones. So observing now collecting the coefficients and discarding the
x y,
so which term?
tensor product h and x y.
No, y1 and y2 are the resulting outputs of the applied, the changed Hadamard qubit.
So this h is 4 by 4, no? H cross h is 4 by 4.
Yeah, this is the first term of 2 by 2 and that's the second.
So this x, what is x? X is in?
X is the input, my input on which I am applying the
So
Hadamard.
it's a qubit.
Yeah, it's a qubit.
So with a qubit, then the h cross h, that will be 4 by 4 and that will be 2 by 1, no? There must be one more thing with there. So this is h cross h, no?
I can just, this is h times and x, this is h times x.
Left hand side.
Then x1, x2. x1, x2. According to your formula, that should be x1, x2.
Which one? Which term?
In the left hand side, h cross h, that should operate on x1, x2.
I'm using the same notation. I'm using where x represents any state according to the binary extension.
But
x could be 0, 1, x could be 0, 1, 1, depending upon how many terms I'm taking in the summation.
so you are writing that as x1, x2.
Yeah.
Okay.
So x is any state, it could be any n bit qubit. N space qubit. So now I collected the coefficient of this psi nu, which I obtained after applying the Hadamard gate. So which is simply mod squared of 1 by 2n summation minus 1 to the power fx. Now if we can come to a conclusion that if my x is any state and n is very very large. So if n is very very large and I am taking the case that the function is balanced, so it should return, let's say 1. I am taking just the output as 1 for half of it and minus 1 for other half of it. Sorry, I'm 0 and 1. 0 and 1. Okay, so I take it as 0 and 1. So I can see this term would vanish if I have fx as 0 for half of the x and for other n by 2 I have it as 1, because the minus 1 factor would cancel the whole summation. And if it is balanced, then of course I would be getting the probabilities as 1. So from simply observing my first n minus 1 qubits, which were my initially 0 tensor itself, qubits, I can simply come to a conclusion using this by observing physically the probability of obtaining the initial state. So it clearly evaluates to 1 if fx is constant or to 0 if it's balanced. So nowhere you can see in the whole algorithm I used fx more than once. I used fx only once and I simply came to a conclusion whether it's constant or not. Now if you have a question that why is it useful, because every problem is not this kind of a thing, but you can reduce the cases to this problem. You can use, reduce many questions or many even factorizing problems to this question whether any function is constant or not. So now we shall see, this is the circuit representation. First applying Heidelberg on the whole state, then applying hidden u of f, which we still have to find what is u of f, and then discarding the second qubit and observing the first ones after applying the Heidelberg. Now using this as a searching algorithm, now we are, let's say for the sake of simplicity here we have 0, 1, 2 to the binary 0, 1 set. The function is defined that way, and we have these 4 data tables where f of these inputs returns 1 for one of the values and 0 for the others. So now again a question is asked to us whether, which fx is that? Fx is what? Which one of these? So this is the kind of searching we have to do. So making a guess similar to the Deutsch Jozsa algorithm, I apply the same analogy. I apply this. I send 2 inputs which will control later on. I assign them and apply Heidelberg to the whole gate and some b of f again. So this is the general form of the application of Deutsch Jozsa algorithm to this searching problem. So now my input is 0 tensor 1, and the state after applying the Heidelberg transform clearly can be seen as this slide. And then I again apply b of f, and it is the same addition, the same modulo 2 addition which I was taking initially in the Deutsch problem. So clearly I can write it this way. After applying the gate b of f, then after applying the gate b of f, I can again discard by correcting the coefficient, I can again discard the global phase and the second qubit using the same treatment. So the last qubit, which was just qubit, we can discard it because that is not really causing any trouble to us for the first part of the qubit, which is the C2 space. So the last qubit is independent of the first two, and those two trash we are left with these possibilities. If we analyze that f of 0, 0 is 1 or f of 0 is 1, f of 0, 0, 1 being implies it is giving me 1 on 0, 0, and same goes for the other 3 inputs too. So analyzing these 4 cases separately, we can write down this tabular form and recall the state of 0, 0 as phi of 0, 0. And what we can observe here clearly is all these states are orthogonal to each other. They are orthonormal clearly. So they are orthonormal, and from our basic quantum circuits and representation of the matrices, we know that any orthogonal states can always be distinguished by using some unitary transformation. So here I apply the same trick, and in this case the circuit or some transformation which is gonna distinguish my states is this U. So U applied on AB will simply give me AB, and so the U of applied on phi of 0, 0 would give me 0, 0 state. So if I apply this U on my first 2 qubits, I would clearly know which state I am observing, because it's clearly with probability 1 being distinguished after all. So that is my physical method of obtaining the state with probability 1. So how do we get U? We can just use a simple trick, let the vectors form the columns of this matrix and then take the conjugate transpose of the whole matrix. I'm going to take the first one, coefficient minus half, 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 half. So this forms my first column, and the rest of the columns I can form the same way. I mean, this is just a trick, but you can find it by letting the coefficient also. So now this state U, I can again use the decomposition of the state U into I mean the postulate, a kind of postulate is that for the decomposition of quantum states, quantum circuits, I can represent any n qubit circuit into single qubit gates and the CNOT gates. So my single qubit gates here are the Hadamard gates, and I have another controlled sigma z gate. After apply these states represented by -1, which are sigma z's, and the control sigma z can again be decomposed into control knots. It is also called the flip gate or sigma z gate. So the complete circuit looks like I have Deutsch Jozsa implementation in the first part, which was this.